Hello everyone, thanks for joining me in this video. I'm Frank. I'm an earth scientist, as well as a hyperspectral geologist, and I like to work with hyperspectral images of rocks and outcrops on Earth and on other planets. As a hyperspectral geologist, you may like to play games. Perhaps while you're hanging out with your hyperspectral friends, you may want to play the hyperspectral game. I mean, why not? If you're not familiar with the hyperspectral game, I will explain it. The aim of the game is to make a mineral map of an airborne hyperspectral image of an unknown area using 4 endmember spectra and a mineral mapping method of your choice. You end the game by comparing the results of the different mapping methods and discuss the differences and similarities. Perhaps you can even agree on the accuracy of the different mineral maps that you produced, and the most accurate map may be appointed. You can do this with your friends or alone. It may sound a bit nerdy, but it's good fun. Here it goes. You download the hyperspectral image here on the left and the 4 spectral endmembers here on the right, and you can start. The hyperspectral image covers an area in southeast Spain with abundant alunite near the town of Guadalquivir. The 4 endmembers provided represent alunite, illite, kaolinite, and limestone, calcite, minerals that are abundant in the area. The image in the center shows in dark tones spectra with deep mineral absorption features. This image didn't come with the download, but was constructed afterwards. So when I played the hyperspectral game, I used 3 different mapping methods: wavelength mapping and decision tree classification, spectral angle mapping, and linear spectral unmixing. Composites of the intermediate products are shown here from left to right of the 3 respective methods. I classified the images in the following ways: a decision tree classifier on the left, a classification following the lowest spectral angle, which means highest similarity, in the middle, and the maximum fraction in a pixel on the right. The mineral maps show similarities and differences, and those may all depend on the choice of parameters, methods, and experience. The fun thing of the game is to discuss the cause of the differences and to define the most accurate map. To appoint the most accurate map, one immediately asks the following questions: how to determine the accuracy, and what's the true mineralogical composition of the surface? Can we use image endmembers or visual interpretation of image spectra to determine the accuracy of the mineral map? Or is it possible to calculate an error image, such as the one commonly created by linear spectral unmixing? Or do we need field spectra that were measured on the ground? Well, this shows that there are lots of possibilities for interesting and very insightful discussions. So I will give you one further clue about the area. Here I'll drape the wavelength map over the terrain in Google Earth. And here you can see the hilly outcrops with bleached rocks in cyan colors that indicate absorption features smaller than 2190 nanometers, indicative of alunite or perhaps pyrophyllite. This coincides with alunite quarries in the area, formed in extensively altered volcanic units.
Ho, ho, ho! Merry Christmas!
Okay. What you can also see here is a limestone cap on the right with layers of sedimentary rock. And they show up in shades of magenta red, indicating absorption features near 2345 nanometers, typical of calcite.
Ho, ho, ho! Merry Christmas!
Okay, alright. I get it. I stop here. I'm explaining too much, and now I'm beginning to spoil the whole point of the hyperspectral game for those of you who want to play it yourselves. And indeed, it is time for the Christmas break. So, the last thing I would like to say in this video: thank you for watching. I wish you happy holidays, a beautiful Christmas, and all the best for the new year. Cheers.